So I want to go over the review practice exam, if you want to call it that. So problem number 1 is to calculate some level curves. So if we have the function z equal x squared plus y squared, this, and we want to look at a window, which is, or a box, which is, let's say, 9 by 9. The level curve z equal 1, so that's all the points where x squared plus y squared equals 1. That's just the circle of radius 1. The level curve z equal 2, x squared plus y squared equals 2. That's the circle of radius square root of 2. We take z equal 4. The level curve x squared plus y squared equals 4. Just the circle of radius 2. We take z equal to 9. The points where x squared plus y squared equals 9. That's just the circle of radius 3, and so on. So those are certain level curves. If we took z equal to 81, x squared plus y squared equals 81, that's the circle of radius 9. So this is all the points where z equals 81. What? If we take the function z equals x minus y squared, and we're looking at a window x going from 0 to 3. This is not drawn to scale. Y goes from -9 to 9. What is the level curve z equals 0? That's where x minus y squared equals 0, or x equal y squared. That's a parabola that looks like this. When x is 0, y is 0. I'm sorry. When y is 0, x is 0. When y is 1, x is 1. When y is 2, x is 4. When y is 3, x is 9. This is, no, not drawing it to scale. Let me draw a little bit better. This is 0, 1, 2, 3. When y is 0, x is 0. When y is plus or minus 1, x is 1. When y is plus or minus 2, x is 4. When y is plus or minus 3, x is 9. Oops, sorry. When y is plus or minus 2, that's a funny window here. It looks like this. Let me do this on a clean piece of paper. So, yeah, I should have made a different box, but The level curves look like this. If we have z equals x minus y squared, the level curve x minus y squared equals 0 is just the horizontal parabola x equals y squared. So this is the level curve, z equals 0. If we look at the level curve, z equal 1, x minus y squared equals 1, that's x equals 1 plus y squared. It's just the same curve, but translated over. And for z equal 2, you would have x equals 2 plus y squared. Look like that. You get a sequence of level curves, which are embedded parabolas looking like that. That's what it is. Any questions about that? For problem 2, we have the function f of xy equals 7x squared y plus e to the xy. So the partial of f with respect to x, 14xy plus y e to the xy. Partial of f with respect to y is 7x squared plus x e to the xy. And if we differentiate twice with respect to x, here's the derivative of f with respect to x. When we differentiate it again with respect to x, we get 14y plus y squared e to the xy. And we want to prove by computation that the mixed partials are the same. So here's the partial of f with respect to y. If I differentiate that with respect to y, so this is the second partial of f dy dx. That means first differentiate by x, that's what we did here, and then differentiate this with respect to y, you get 14x plus xy e to the xy. Here I have the derivative of f with respect to y. If I differentiate that, then with respect to x, I get 14x plus xy e to the xy. And if you compare the two of them, they're equal. Second partial of f with respect to y and x is the same as the second partial of f with respect to x and y. So that's what it means to prove by computation that these mixed partial second derivatives are the same. Right? Any questions about that? Problem 3 is to compute derivatives of two composite functions. So we have w is a function of x and y. It's equal to x cubed y minus 2x squared y to the fifth. And x is a function of t, e to the t, and y is a function of t, it's t squared. So you want to compute dw dt. And by the chain rule, because if you plug in x and y, w is just a function of t. dw dt is the partial of w with respect to x, dx dt, plus the partial of w with respect to y, dy dt. If we differentiate this with respect to x, we get 3x squared y minus 4x y to the fifth, dx dt, which is e to the t, plus partial of w with respect to y, which is x cubed minus 10 x squared y to the fourth dy dt, which is 2t. And we want to compute this when t is equal to 1. Well, when t is 1, x is e to the first power, or e, and y is 1 squared, which is 1. So at t equal to 1, dw dt is equal to 3 x squared y minus 4 x y to the fifth times e to the first power plus x cubed is e cubed minus 10 x squared, that's e squared, y, which is 1, times 2t, which is 2 times 1, which is 2. So we get 3e cubed minus 4e squared plus 2e cubed minus 20e squared is 5e cubed minus 24e squared. So if I did my calculation correctly, that's the answer. Okay. Part B is another calculation using the chain rule. We have the same function w, x cubed y minus 2x squared y to the fifth, but now x is a function of s and t, s squared plus t, and y is a function of s and t, s minus t squared, and we want to find the partial of w with respect to s, which is the partial of w with respect to x, partial of x with respect to s, plus the partial of w with respect to y, partial of y with respect to s. Partial of w with respect to x, we already calculated, that's 3x squared y minus 4x y to the fifth. Partial of x with respect to s is 2s. Plus the partial of w with respect to y, which is x cubed minus 10 x squared y to the fourth times the partial of y with respect to s, which is 1. And when s and t are both equal to 1, x is equal to 1 squared plus 1, which is 2, and y is 1 minus 1 squared, which is 0. So at s equal t equal 1, the partial w with respect to s is, let's see, all of the terms that involve a y are 0, so we're just left with x cubed, which is 2 cubed, which is 8. So if I did the arithmetic correctly, the answer is 8. Any questions about this?
Professor, can you move the paper over a little bit?
Move it over. I'm not sure which way.
Like to see the right side. Yeah, that's perfect. Thank you.
Yeah. Okay, well, that was problem 3, which suggests that the next problem is problem 4. So problem 4, we have a function z is the log of x squared minus y. So that is the gradient of this function. So it's the partial derivative of z with respect to x. It's a vector partial of z with respect to y. When I differentiate this with respect to x by the chain rule, from Calc 1, I guess, this is 1 over x squared minus y times the derivative of x squared minus y with respect to x, which is 2x. When I differentiate this with respect to y, I get 1 over x squared minus y times the derivative of this with respect to y, which is minus 1. So that's the gradient, and let me call this f of xy. So the gradient of f evaluated at the point 2, 3 is equal to, when x is 2, this is 4, x squared is 4 minus 3 is 1, so that's just 4, and 4 minus 1, that's the gradient. And the directional derivative at the point 2, 3 in the direction of the unit vector u, where u is the vector 1 over root 2, 1 over root 2, is simply the dot product of the gradient of f at 2, 3, dot product with this vector. So that's the dot product of 4 minus 1 with the vector 1 over root 2, 1 over root 2. So that's 4 over root 2 minus 1 over root 2, which is 3 over the square root of 2. Or if you don't like roots in the denominator, 3 root 2 over 2. They're equally valid. So that is the directional derivative of f at the point 2, 3 in the direction of this unit vector. The function is log of x squared minus y. The gradient is the partial derivative with respect to x, comma, partial with respect to y. And when you evaluate this at 2, 3, the denominator is 1. So you just get 4 minus 1. And the dot product of that with this unit vector is 3 over root 2. So this is A, and this is B. Huh. Problem 5 was another problem to compute a directional derivative. Here, the function f of xy is equal to the square root of 4 minus x squared minus 2y, or 4 minus x squared minus 2y to the power 1/2. So the partial of f with respect to x is 1/2 4 minus x squared minus 2y to the minus 1/2 times the derivative of this with respect to x, which is minus 2x. The 2's cancel, so this is minus x over the square root of 4 minus x squared minus 2y. And if I take the partial derivative with respect to y, that's 1/2 4 minus x squared minus 2y to the minus 1/2 times minus 2, which is minus 1 over the square root of 4 minus x squared minus 2y. And if I want the partial derivative, if I want the gradient at 2, 2, so at the point xy equal to 2 minus 2, let's see, what is that? When x is 2, this is 4. When x is minus 2, when y is minus 2, minus 2y is plus 4. So I get 4 minus 4 plus 4. So this denominator is 4, square root of 4, which is 2. So this is minus 2 over 2, or minus 1. Right? Plug in y equals minus 2. x equal plus 2. You get square root of 4, which is 2, and 2 over 2 is minus 1. And this is going to be minus 1 over 2. This is 2. So the gradient of this function at the point 2 minus 2 is the vector minus 1 minus 1/2. And if I want the directional derivative in this direction of now the vector u is 1 over root 5, 2 over root 5, that's going to be the dot product minus 1 minus 1/2, dot product with the vector 1 over root 5, 2 over root 5. So that's minus 1 over root 5 minus 1 over root 5 is minus 2 over the square root of 5. So if I do my arithmetic correctly, if the gradient is minus 1 minus 1/2, and I'm taking the dot product with the unit vector 1 over root 5, 2 over root 5, I get minus 1 over root 5 minus 1 over root 5 is minus 2 over root 5. And that's what it is. Any questions about this? Okay. In problem 6, we have a function f of x, y, z equal x squared plus y squared plus z squared. We have the level surface f of x, y, z, or x squared plus y squared plus z squared equals 9. So in 3 dimensions, that's just a cube centered at the origin with radius 3. That's what our surface looks like. And on this surface, there's the point 2 minus 2, 1. Because if you compute f of 2 minus 2, 1, you get 2 squared plus minus 2 squared plus 1 squared is 4 plus 4 plus 1, which is 9. So the point 2 minus 2, 1 lies somewhere on the surface. And we want to find a unit normal vector to the surface and an equation of the tangent plane. So a normal vector will be the gradient of the function at any point x, y, z on any level surface. The gradient of the function is what? What is the gradient of this function? You take the partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. When you differentiate this with respect to x, you get 2x. When you differentiate this with respect to y, you get 2y. When you differentiate it with respect to z, you get 2z. So the gradient of f at the point 2 minus 2, 1 is the vector 2 times 2, 4. 2 times minus 2, minus 4. 2 times 1, 2. But of course, this is not a unit vector. You take the length of this vector, that's the square root of 4 squared plus minus 4 squared plus 2 squared. That's the square root of 16 plus 16 plus 2. That's, sorry, plus 4. That's the square root of 36. That's 6. So this vector has length 6. So a unit vector normal to the surface at the point 2 minus 2, 1 is the vector u, which is 1/6 times the gradient, or 1/6 times the vector 4 minus 4, 2, which is scalar multiplication. This is 2/3 minus 2/3, 1/3. So this is a unit vector normal to the surface. So if you think of it as, here's your surface, here's the point 2 minus 2, 1. You have this normal vector n, or u, right? Perpendicular to the surface at that point. The tangent plane will have satisfy the equation. So if you take any vector x, y, z, the vector from 2 minus 2, 1 to x, y, z has to be perpendicular or orthogonal to u. So you have to satisfy the equation u dot x minus 2, y minus 2, z minus 1 is 0. That is, 0 is equal to 2/3 minus 2/3, 1/3. Dot product with x minus 2, y plus 2, z minus 1. So this is 2/3 x minus 2 minus 2/3 y plus 2 plus 1/3 z minus 1 equals 0. If I simplify this and multiply by 3, I can just multiply by 3 and cancel all these 3's. I get 2x minus 2 minus 2x minus 4 minus 2y minus 4 plus z minus 1 equals 0, or 2x minus 2y plus z equals 9. So this is the equation of the tangent plane. To my surface at this point. Okay. So this involves a fair amount of vector calculus to understand what's going on here and why. So a normal vector to a surface is a unit vector in the direction of the gradient vector, a unit normal vector. Any questions about this? Okay, let's see. Problem 7. In problem 7, we have a function of two variables, f of x, y equals y over x. If you let x equal 1 and y equal 2, f of 1 comma 2 is 2 over 1, or 2. So the point, call that z. So the point 1, 2, 2 lies on the surface. Well, it lies on the graph of the function. It lies on the surface. Z equal f of x, y. We want to find a unit normal vector to the surface at this point. and an equation of the tangent plane. So this straightforward way is to say, suppose we look at the function, call it g of x, y, z, which is f of x, y minus z, or y over x minus z. So g at 1, 2, 2 is equal to 2 over 1 minus 2, which is 0. So 1, 2, 2 lies on the level curve g of x, y equals 0. And we can compute the levels, the tangent plane to the surface by looking at this surface as the level curve of this function of 3 variables. For this function, what is the gradient? The gradient of g is the partial of f with respect to x minus y over x squared, partial of f with respect to y, partial of f with respect to z. So the gradient of g at the point 1, 2, 2 is equal to minus 2 over 1, which is minus 2, 1 over 1, minus 1. So the equation of the tangent plane will be the gradient dot product with x minus 1, y minus 2, z minus 2. Or this is the vector minus 2, 1, minus 1. So we're taking the dot product of this with this. We get minus 2 times x minus 1 plus 1 times y minus 2 minus 1 times z minus 2 equals 0. Minus 2x plus 2 plus y minus 2 minus z plus 2 equals 0. So that's minus 2x plus y minus z equals minus 2, or 2x minus y plus z equals 2. So this is the equation of a plane. You can check if you let x equal 1, y equal 2, and z equal 2, you get 2 minus 2 plus 2 equals 2 equals 0. So this is the equation of the tangent plane. Now, that's the most straightforward way to do it. An equivalent way, which is obtained from this, is that if you have a function z equal f of x, y, the equation of the tangent plane at the point AB is equal to z equals the partial of f with respect to point y at the point AB times x minus a plus the partial of f with respect to y at AB times y minus b plus the value of the function at AB. And we're looking at the point AB equal to 1, 2. So the partial of f with respect to x is minus y over x squared. So z is equal to, well, so minus y over x squared, x minus 1. Partial of f with respect to y is 1 over x, y minus 2, plus the value of the function, plus the function. So at AB, when you're letting x equal 1 and y equal 2, you get z equal minus 1, x minus 1, plus 1, y minus 2, plus y over x, which is 2. Let's see, y over x squared is 2. This is minus 2. which is exactly what we got here. Minus 2x plus y, 2 minus 2 plus 2. It's exactly the same equation. It's just a slightly different derivation. Any questions about this? Okay. After 7 comes 8. So we have a function f of xy equal to x squared plus xy plus a half y squared minus 2x plus y plus 5. And we want to find the local maxima and local minimum of this function using the critical points in the second partial derivative test. So x squared plus xy plus a half y squared minus 2x plus y plus 5. So the partial of f with respect to x is equal to 2x plus y minus 2. And the partial of f with respect to y is equal to x plus y plus 1. So you have a critical point at a point where both partial derivatives are 0. So you want to find, so the AB is a critical point if 2a plus b minus 2 is 0, a plus b plus 1 is 0. So we're back to high school algebra solving two equations and two unknowns. This is the same as 2a plus b equal 2, a plus b equal 1. So we have to solve these equations. If you subtract the second equation from the first, you get a equal 1, and if a equal 1, b equals 0. So it looks like there's only one critical point, 1 comma 0. So let me just double check that. We have x squared plus xy plus a half y squared minus 2x plus y plus 5. The partial derivative with respect to x is 2x plus y minus 2. The partial derivative with respect to y is x plus y plus 1. So a point AB is a critical point if both partial derivatives are 0. So 2a plus b equals 2. A plus b, oops, I made a mistake. That's always good. A plus b plus 1 equals 0 means a plus b equals minus 1. So if I subtract the second equation from the first, I get a is equal to 3. And if a is equal to 3, b is equal to minus 4. Right? 3 minus 4 is minus 1. 6 minus 4 is 2. So the one critical point is AB equals 3 minus 4. So now we apply the second derivative test. So we have to compute the three partial derivatives of this function. The second partial derivative of f with respect to x. If I differentiate this with respect to x, I get 2. If I take the partial derivative with respect to x, and then I differentiate it with respect to y, I get 1. if I take the partial derivative with respect to y and differentiate it with respect to x, I know what I'm going to get, but if I do it in any case, I get 1. And if I differentiate twice with respect to y, I get 1. So my determinant d that I have to calculate is 2, 1, 1, 1. This determinant is equal to 1. So the determinant, so this number d at the point 3 minus 4 is 1, which is positive. So 1 is positive. The second derivative at the point 3 minus 4 is equal to 2, which is positive. This positive means we have a local minimum at the point 3 minus 4. So this is the analog of the second derivative test for a function of two variables. Any questions about this? Okay. And the next three problems, or the last three problems, I think, are calculating some integrals. So problem 9 is a double integral, but we're giving it as an iterated integral, which makes it a little bit easier. So we have the integral from 0 to 3 with respect to y of the integral from -2 to 1 with respect to x of the function 2x plus 3y. So just look at this inside integral. This is the integral from -2 to 1, 2x plus 3y dx. When you integrate 2x with respect to x, you get x squared. When you integrate 3y with respect to x, 3y is just a number, a constant. You get 3y times x, or 3xy. And I'm evaluating that from x going from -2 to x going to 1. So when x is 1, I get 1 plus 3y. And when x is -2, I get 4 minus 3 times x is minus 6y. So this is -3 plus 9y. That's this inside integral. So I'm integrating from 0 to 3 of -3 plus 9y dy. That's -3y plus 9 halves y squared, as y goes from 0 to 3. When y is 3, I get -9 plus 81 over 2, and y is 0, I get 0. So this is -9 plus 81 over 2. 81 minus 18 is 63 over 2, I believe. So if I did my arithmetic or my integration correctly, that's the answer. Okay. So when I integrate 2x plus 3y with respect to x, I get x squared plus 3xy, evaluated from -2 to 1. X goes from -2 to x goes to 1. So when x is 1, I get 1 plus 3y. When x is -2, I get 4 minus 6y. That's -3 plus 9y. I'm integrating that with respect to y. -3y plus 9 halves y squared. When y is 3, this is -9. This is 81 over 2, 63 over 2. Okay. In problem 10, we have a double integral over a region R of x cubed plus xy dA, and the region R is the set of all points xy where x is between 1 and 2, and y is between 1 and -1. So that's the region in the plane. X goes from 1 to 2, y goes from -1 to +1. So this is my region R. So if I want to write this as a double integral, I can integrate first with respect to x and then with respect to y, or first with respect to y and then with respect to x. It's my choice. Let's say I integrate first with respect to x and then with respect to y. So x goes from 1 to 2, and y goes from -1 to +1. So we'll try the integration in that order. And what I'm integrating is x cubed plus xy. Now, let me do it on a clean sheet of paper. So I want to actually do the integral in two different ways. So my region R is x is from 1 to 2, and y is from -1 to +1. So the double integral over R of my function x squared plus xy dA, if I'm going to integrate first with respect to x, so the function is x squared plus xy, x goes from 1 to 2, and then I'm going to integrate that with respect to y from -1 to +1. So this integral on the inside, the integral from 1 to 2 of x squared plus xy dx, the integral of x squared is a third x cubed, and the integral of xy is a half x squared y. And I'm integrating that from 1 to 2. So when x is 2, this is a cubed. And when x is 2, this is 4 over 2, 8 cubed plus 2y. When x is 1, this is 1/3 plus a half y. So this is 8/3 minus a third, 7/3, 2 minus a half, plus 3/2 y. So this is the integral of 7/3 plus 3/2 y from -1 to 1. Let me just do that over here. So this double integral, x squared plus xy dA, is now the integral from -1 to 1 of 7/3 plus 3/2 y dy. That's 7/3 y. The integral of y is a half y squared, so this becomes 3/4 y squared, evaluated from -1 to 1. When x is 1, this is 7/3. When y is 1, it's 7/3. When y is -1, it's -7/3. So 7/3 minus 7/3 is 14/3. And when y is plus or minus 1, you get the same thing. This cancels. So it looks like the answer is 14/3. So I want to actually check that by doing the integral as an iterated integral, but in the opposite order. So for this function x squared plus xy dA, I want to integrate now first with respect to y, and then with respect to x. So y goes from -1 to 1, x squared plus xy, and with respect to x, from 1 to 2. So what is this inside integral here? The integral from -1 to 1 of x squared plus xy dy is x squared y plus a half xy squared, evaluated from -1 to 1. When y is 1, I get x squared. When y is -1, I get minus x squared, so I get x squared minus x squared. That's 2x squared. Here, when y is plus or minus 1, I get the same thing. I get a half x minus a half x. So this inside integral is just 2x squared. So if this is correct, this is the integral from 1 to 2 of 2x squared dx. That's the integral from 1 to 2. Sorry, that's 2/3 x cubed from 1 to 2. That's when x is 2, this is 8 times 2. This is 16/3 minus 2/3 is 14/3. So it's nice to see that I got the same result doing the problem in two different ways. And that's good. Questions about that? So the simplest integrals are integrals over rectangles. But more generally, we might have an integral where you have two curves and you're integrating over a region between two vertical lines, but bounded above by one curve or another. And so if you have a region R, this is say A and B. So if you're looking at the region X between A and B, and for all X between A and B, Y is bounded above by a curve H of X and below by a curve G of X. So for every X between A and B, Y is between G of X and H of X. That's the general region over what integrates. And that's exactly what we have in problem 11. We have a double integral over a region R of the function xy dA, where R is bounded by x equals 0, which is the y-axis, y equal 2x plus 1, and y equal minus 2x plus 5. So let's see what that region looks like. So this is the line x equals 0, just the y-axis. The line y equal 2x plus 1 has y-intercept 1 and goes up with slope 2. This is y equals 2x plus 1. The line y equal minus 2x plus 5 has y-intercept 5 and goes down with slope minus 2. This is 5 minus 2x. And the region bounded by this line, and this line is this triangular region. You see, this is 1, this is 5. This is the point 1, 3. So we can also describe this region as follows. This is the region where x is between 0 and 1, and y is bounded above by the line 5 minus 2x, that's my function h of x, and below by the function y equal 2x plus 1, that's my function g of x. So this integral is a double integral with respect to x, x goes from 0 to 1. But with respect to y, y goes from the bottom, 2x plus 1, to the top, 5 minus 2x, and we're integrating the function xy. So this is the important first step. You can't solve the integral until it's set up properly. It's an integrated integral. This is the inside integral. Let me do that. So the integral of xy with respect to y is 1/2 xy squared. Right? If you take the partial derivative of this with respect to y, you get xy. And we're integrating from y equal 2x plus 1 to y equal 5 minus 2x. So this is 1/2 x y squared, 5 minus 2x squared, minus 1/2 x, 2x plus 1 squared. So I need to do a little bit of high school algebra to simplify this. This is, I have 1/2 x, which I can factor out. 5 minus 2x squared is 25 minus 20x plus 4x squared, minus 2x plus 1 squared. So this is minus 4x squared plus 4x plus 1. So I get 25 minus 1 is 24 times 1/2 x. That's 12x. I have minus 20x minus 4x is minus 24x times 1/2 x squared is minus 12x squared, and 4x squared minus 4x is 0. So this inside integral is 12x minus 12x squared. So this is the integral from 0 to 1 of 12x minus 12x squared. The integral of 12x is 6x squared, and the integral of 12x squared is 4x cubed. I'm evaluating that from 0 to 1. That's 6 minus 4, which is 2. So the value of this integral is 2. And again, it has to be set up properly. You have to be able to draw the region and calculate the integral.
Professor, can you explain how you got 0 and 1 again, please?
Yeah. So my region R. So this is what the problem says. The region R is bounded by the curves or the equations, the lines, x equals 0, y equal 2x plus 1, y equal minus 2x plus 5. So we have to figure out what is this part of the plane. So what is x equals 0? X equals 0 is the y-axis. That's all the points with x equals 0. What is y equal 2x plus 1? That's a straight line with y-intercept 1. And slope 2. It's just this line. So this is y equal 2x plus 1. Minus 2x plus 5 That's a line with y-intercept 5 and slope -2. That's this line. Where do these lines intersect? When x is 1, y is 3. When x is 1, y is 3. This is the point 1, 3. So the region bounded by these three straight lines, it's this triangle. And this triangle, x, for every point in this triangle, x is between 0 and 1. And y is below or on this line and above this line. So that's
Thank
how I
you.
worked out the structure of this region. Does that make sense? Or is that?
Yes, thank you.
Yeah, okay. And the second integral in this problem, and I think that's the last problem. Oh no, there's one more problem. Okay, good. This is the second integral, which is double integral over some region R of the function 12y, where R is bounded by y equals 0, y equal 2 minus x, and y is the square root of x. So let's see what that looks like. Of course, it's only defined for x positive or 0 because the square root. So when y equals 0, it's just the x-axis. Y equal 2 minus x is just the line with y-intercept 2 and slope -1. Oops. Stop sloppy. Okay. It's just this line. This is the line y equal 2 minus x. The square root function, y equal the square root of x. At 0, it's 0. At 1, it's 1. At 4, it's 2. Square root function looks like this. And where do they meet? Well, they intersect when x is 1. Square root of 1 is 1. 2 minus 1 is 1. So the region where they intersect is this region. It's not a triangle. This is a straight line. This is a straight line, but this is a curve. So we want to integrate this function over this region. Now, let's see, this point is 2. Right? So how do you describe this region R? So you could say, well, x is between 0 and 2, and y is bounded below by 0, but its upper bound depends on whether x is between 0 and 1 or x is between 1 and 2, right? So you could say that you have for 0 less than or equal x between 0 and 1, y is between 0 and the square root of x. And for x between 1 and 2, y is between 0 and 2 minus x. So if you want, you could write this as two integrals, because you have separate descriptions for the left and the right halves of this region. You could say if you integrate, is the integral of 12y, you could first integrate with respect to y, dy, from 0 to the square root of x, and then integrate that with respect to x from 0 to 1, plus when you're integrating with respect to x from 1 to 2, you're integrating with respect to y from 0 to 2 minus x of your function. So you would have to, using this description, you would write your integral as a sum of two different integrals. So you have to do two different calculations, which is okay. I'll do that maybe in a moment. But in this case, you can look at this area differently. You can see, if you look at this as a function, if you look at this, you see y is between 0 and 1. So an alternate way to describe this region is y is between 0 and 1. And for each y, x is from here to here. What is the lower curve? When y is the square root of x, that's the same as saying x equals y squared. So for each y from 0 to x starts at y squared and goes up to here. When y is 2 minus x, that's the same as saying x is 2 minus y. It's the same equation. So x goes from y squared up to 2 minus y. And then I could also write this is as not just one integral. I'm going to integrate with respect to y from 0 to 1. And for each y, I'm integrating x from y squared to 2 minus y dx. And my function is 12y. So I just have one integral to do. What is this inside integral? The integral of 12y with respect to x is just 12xy. So if I'm integrating this from x equal to y squared to 2 minus y, this is from x equal y squared to 2 minus y. This is 12, 2 minus y times y, minus 12y squared times y. So this is equal to 24y minus 12y squared minus 12y cubed. So this is the integral from 0 to 1. 24y minus 12y squared minus 12y cubed dy. The integral of 24y is 12y squared. The integral of minus 12y squared is minus 4y cubed. The integral of minus 12y cubed is minus 3y to the fourth. So I'm integrating that from 0 to 1, which is 12 minus 4 minus 3. So I get 5. That's the answer. So here I had a choice. I could think of this region as saying x goes from 0 to 2, and y goes from 0 to this curve or from 0 to this line, depending on whether x is between 0 and 1 or 1 and 2. Or I could just reverse my way I look at this. I could say y is between 0 and 1, and for each y, x goes from 2 minus y up to y squared. And the second way gave me just one integral to do, and it was pretty easy. But if I compute both of the integrals from the first method, I get exactly the same answer, because there's only one answer. Right? Yeah. So these are types of problems that might be on the exam. I don't know for sure because I haven't made up the exam yet, but certainly you should. Oh, I'm sorry, I have one more problem to do. This was problem 11, and there is also problem 12. So this is an interesting problem. So problem 12 is the following. Find the volume of the solid tetrahedron bounded by the coordinate planes x equals 0, y equals 0, z equals 0. So in 3 space, the xy plane is the coordinate plane with z equals 0. The xz plane is the coordinate plane y equals 0. And the yz plane is the coordinate plane x equals 0. So we're looking at the first quadrant or the first octant bounded in by these 3 coordinate planes and the plane z equal 8 minus 2x minus 4y, or 2x plus 4y plus z equal 8, right? What does that plane look like? This is 8, and this is 4, and this is 2. So we have this solid figure. It's a tetrahedron. This is the base and this is the height, right? We have this tetrahedron and we want to find the volume of it. So to get some idea of what this is, you really need to sketch these pictures because you have this plane, z equal 8 minus 2x minus 4y, or 2x plus 4y plus z equal 8. And where does this plane cut the coordinate axes? When x and y are 0, z is 8. When x and z are 0, y, 4y equals 8, y is 2. When y and z are 0, so you're on the x-axis, 2x equals 8, so x is 4. So we have this tetrahedron bounded by the coordinate axes and this plane. And we want to find its volume. So we have this function, f of xy, which is my z, 8 minus 2x minus 4y. And the volume is just the integral of this function over this triangle. What is this triangle that we're looking at? In this triangle, x goes from 0 to 8, 0 to 4, and y goes from 0 to 2. This triangle, right? We're integrating this function over this triangle. All right? In this triangle, x is between 0 and 4. And y is what? Well, y is the line 2 minus, this line is slope minus a half x. Right? When y is 0, it's 2. When y is 4, it's 0. So this is my region R. So the volume is going to be the integral with respect to x from 0 to 4. The integral with respect to y from 0 to 2 minus x over 2 of my function h minus 2x minus 4y. So let me compute first my inside integral. The integral of 8 minus 2x minus 4y with respect to y is 8 minus 2x times y minus 2y squared. That's the indefinite integral. And I'm integrating from 0 to 2 minus x over 2. Y equals 0 to y equals 2 minus x over 2, which is the same as 4 minus x over 2. So what do we get? This, by the way, this is the same as 2 times 4 minus x. So I get 2 times 4 minus x times 4 minus x over 2 minus 2 times 4 minus x over 2 squared. So this is 4 minus x squared. This is 4 minus x squared over 4 times 2 over 2. So this is 4 minus x squared over 2, which is 16 minus 8x squared plus x squared over 2. So this is 8 minus 4x squared. Let's see. 16 minus 8, yes. 8 minus 4x squared plus a half x squared. That's my inside integral. So this is the integral from 0 to 4 of 8 minus 4x squared plus a half x squared dx. Integrating with respect to x, I have 8x minus 4/3 x cubed let's see what I do here. 4 minus x squared. It's 16 minus 8x plus x squared. So that's 4 minus 4x. That should just be a 4x plus a half x squared. So this is 8x. The integral of 4x is 2x squared. And the integral of a half x squared is a 6x cubed, evaluated from 0 to 4. So 8 times 4 is 32. 4 times 4 is 16 times 2 is minus 32 plus 4 cubed over 6. That's 64 over 6. So I get 32 over 3. Yes, and that's the answer. That's the volume of the tetrahedron. Okay, that's the review sheet. So again, I remind you, exam is 11 o'clock Wednesday morning, room 203 in Gillette. And if you have questions, I strongly encourage you to log on to one of the problem sessions. There's one today at 7 in the evening and one tomorrow at 7. And I'm also available other times to answer questions if you send me an email. Any questions for the day? It's a beautiful day, I think, so hope you get to enjoy it a little bit, and see you Wednesday. Bye all.